Okay guys, we're going to talk about chapter 18, which is equilibrium. The first thing we got to get to is the fact that almost all reactions are reversible. So up until now we've said that nitrogen plus hydrogen will make ammonia, and we've been pretending as if ammonia can't decompose and come backwards. But in reality, all chemical reactions can go pretty much forward and backwards. And so if we were to run this equation and calculate the concentration of the three compounds in there, the reactants are going to go down, the product's going to go up, but they're going to reach a point where they stop changing. And notice how the reactants didn't go down to 0, and the product isn't the only thing left. So they get stuck at equilibrium. Okay? And these numbers can change depending on how much you started with, but the ratio of them is always a fixed number, which we will get to in a minute. So the key thing is to remember, nothing is as simple as this plus this makes that. You always get both the forward direction and the reverse reaction at the same time. So now I'm going to move over here, okay, and explain kind of what equilibrium is. Okay, so it's important to remember that equilibrium is dynamic. Okay, so what that means is every single time one forward reaction happens, one reverse reaction happens. It's not just sitting there doing nothing. You still have chemistry happening, and it's very similar to what we talked about earlier with if you have a jug with water in it, the water is constantly evaporating, but every time one evaporates, another one from the vapor condenses. So to our eyes, it looks like the volume is not changing and there's nothing happening. But in reality, it's constantly cycling, and that's the same thing for any chemical reaction. You still have forward reaction happening, and you still have reverse reaction happening, but their rates are equal to each other. So from chapter 17, if it ever gives you the rate of one of the reactions, and it tells you it's at equilibrium, that number is also the rate of the reverse reaction. Okay? So now I'm going to slide down here, and we're going to talk about how to come up with our equilibrium expressions. Okay? So basically any equation can be basically represented with just letters. So we still have our products on the right, our reactants on the left. The little letters here are the coefficients from your balanced equation. The big letters are your chemical formulas. The trick is, for equilibrium, it's similar to enthalpy, but instead of it being subtractive, it is division. And so what we do is, instead of it being for delta H, it was the products minus the reactants. For equilibrium, it's always the products divided by the reactants. So what we have is our concentration of our product, C, raised to the coefficient, the little c, times our concentration of D to the little d power, divided by concentration of A to the little a times the concentration of B to the little b. This is how you create your equilibrium equation for any chemical equation. So just remember, it's always the concentration of the products raised to their coefficients divided by the concentration of the reactant raised to their coefficients. Okay, so now here's an example that the book does for you. We're going to walk through it together. Okay, so on the product side, we have ammonia. So our equation for this is going to be the concentration of NH3 to the second power divided by the concentration of N2 to the first power, because it's just a 1, times the concentration of H2 cubed. Okay, and from this point, the problems are going to give you either all 3 of these numbers and ask for KEQ, or it'll give you KEQ and everybody except 1 and ask you to solve for that one variable. If you want to call that element X or that compound X and solve it like that so it matches what you do in math, that's fine. Or you can continue to leave it as like N2 so that when you get to the end, you know that that number is a concentration of nitrogen. Okay? We'll do some of those in a little bit, but right now I want to just go over some things to remember. So the book has a whole section on homogeneous equilibrium versus heterogeneous equilibrium. Those are 2 vocab words that are important. Okay, but at the end of the day, you just have to remember, okay, we can't calculate equilibrium without that substance or that measurement being able to change. And so what happens is gases can change their concentrations very, very easily. We can put more gas in the same container, we can take gas out, okay? We can do lots of stuff with the gas. Aqueous solutions, and of course I spelled that wrong, E-O-U-S, right? Aqueous solutions can also change their concentrations. That's why we had to learn how to measure molarity, molality, all of the stuff we did with aqueous equations, but these 2 can change their concentration. Solids cannot and liquids cannot. If you have liquid water, it doesn't matter if it's a gallon of it or even a couple of little ounces of it, it always has its same molar mass and its molar volume, and it's like that's why those definite volumes mattered back when we learned the properties of solids and liquids. So what that means is that you can ignore any solid or any liquid when you are doing these equations. So for example, if we have Na solid plus Cl2 gas at equilibrium with NaCl solid, and we'll put a 2 there and a 2 there, okay? You don't have to create an equilibrium constant with the sodium chloride or the sodium because they're both solids. So the KEQ for this one would just be, there's nothing over there that we care about, so 1 divided by the chlorine gas is the only thing that would affect the rate or the equilibrium of this reaction. And so it really makes it simple. If it's a solid or a liquid, it doesn't count. From there, you just plug it in, and then you can start doing the math problems. All right, and now we're going to do an example problem of how to calculate an equilibrium constant for a chemical equation if you're given concentrations at equilibrium. And so this number right here tells us that at equilibrium we have 0.2485 molarity hydrogen, we have 0.2485 molarity of iodine, and we have 1.7515 molarity of hydrogen iodide. So what that means is that you first have to just build your equation for the equilibrium constant based off of our chemical equation. So just like before, it's the products raised to the coefficient divided by the reactants raised to their coefficients. But because these are ones, you don't have to worry about it. And from there, because those 3 are equilibrium concentrations, you can just plug them in for the correct substance. So we get 1.7515 squared divided by 0.2485, and I'm going to put a square next to it because they're both the same. So if you type that in on your calculator, you should get 49 49.70. Okay? And again, I don't need you to give me any units on equilibrium on case. Okay? They're super complicated. All that matters is the number. And this number is a very large number. So the number we want to compare it to is the number 1. So if your KEQ is ever greater than 1, then it favors the products. And if your KEQ is ever less than 1, it favors the reactants. So this answer is 50, which is way larger than 1. So that tells us that this reaction wants to be on the right side, not the left side. So that's an example of how to do it. We could have easily given you the 49.7 and erased this I2 and asked you to solve for I2. You would still build this equation. You would substitute the 49 in there, you'd substitute the two numbers that you know, and then you would just solve for I2, just like you would in math. But if we did that, you would get 0.2485.